Hello everyone and welcome back to our numerical method series. In today's video, we will dive into one of the most practical and visually intuitive techniques used to find the roots of a nonlinear equation, that is a secant method. So whether you are just a student, an engineer, or just curious about numerical techniques, this method will sharpen your understanding of iterative root finding algorithms. So stay tuned because we will also break down the graphical representation for a clearer conceptual grasp. So we have to construct a graph. Okay, so this is our y-axis and this is our x-axis and this is our graph. And here we have point P naught and here we have point P1. At this point, the graph touches x-axis and this is basically the root of the equation and we need to target that. Okay. So the secant method is an iterative numerical technique that is used to find the root of nonlinear equation and we just call it y is equals to f of x that is equals to 0. So unlike the Newton-Raphson method which uses the derivative, the secant method just approximates the derivative using two previous points on the curve. Now let's take a look at this graph. We start with two initial guesses, that is P0 and P1, that is located on the x-axis. These are the points where we evaluate the function f of x, giving us the corresponding function values f of P0 and f of P1. Using these 2 points, we draw a secant line, a straight line that connecting this P0 to P1. So this means that we have 2 points P0, f of P0 and P1, f of P1. So this line is then extended to intersect the x-axis and the x-intercept of this secant line becomes our next approximate and we call it P2. And this is how we iteratively generate new points. So the generic formula used for secant method is Pn plus 1 that is equals to Pn minus 1 f of Pn minus Pn f of Pn minus 1 divided by f of Pn minus f of Pn minus 1. So we then repeat the same process and draw a new secant line between P1 and P2. So here we have a P2 and we just connect P1 to P2 again like this. And this is our new approximate root and we call it P3. So by drawing this, we will get a new point P1, f of P1 and P2, f of P2. So find its x-intercept which becomes P3. Continue iterating, we will get P4, P5 and so on. If we draw another one, so we connect P1 with P3 just like this. So we get a new approximate root and we call it a P4. If we target out again, so we just connect this line with this point, and we got another approximate root, that is P5, and so on. So in this diagram, you can see that the points gradually converging forward towards the actual root of the function. So each new secant line gets closer and closer to the x-axis where f of x is equals to 0. So this visualization makes it clear that how the secant method works without needing a derivative. So the points that we take away from this graph is number one, secant line approximate tangents. So secant line approximate tangents without needing any calculus. Secondly, this method requires only function value, and not its derivative. Thirdly, it converges faster than bisection. Faster than bisection method, but usually slower than Newton-Raphson method. And the last one is, if the guesses are good, it leads to quick convergence. So we just simply write it. Guesses are good, it leads to quick convergence. So if the guesses are good, it leads to quick convergence as shown by P2, P3, P4, P5 that approaching to the root. So to wrap up, the secant method is a beautiful blend of a geometry and algebra, relying only on two guesses and the shape of the function to locate a root. Graphically, it's intuitive. Just draw secant line and watch them steer you to the solution. We will explore the working rule of the secant method, an elegant and powerful algorithm used to find the roots of a nonlinear equation. So all without needing the derivative. So let's get into the step-by-step logic, the math, and the strategy behind the amazing technique. In many mathematical models and engineering problems, we encounter equation of the form f of x is equals to 0. So where we cannot solve the equation algebraically, that's when we turn to iterative numerical methods like bisection method, Newton-Raphson method, and of course the secant method. So the secant method is specifically useful, number one, when we can't compute the derivative of any function. Secondly, we need a fast and relatively simple method to find the root. Need a fast and simple method. So the basic concept of the secant method is that instead of using the derivative like Newton-Raphson method, the secant method uses two initial approximations. So let's call them x0 and x1. These are two values where the function f of x is defined. So basically, we need to evaluate the function at these 2 points, that is x0 and x1, and then we draw a secant line through these 2 points on the graph of f of x, and the point where this line intersects the x-axis is our next approximation, and we denote it as x2. And that's the basic idea. At each step, we use the two most recent approximations to estimate the next one. So iteratively improving our guess of the root. So let's derive the very simple formula for our secant method, that a very simple derivation, just a 2 to 3 lines derivation. So a secant line passes through 2 points, and we call it x naught and f of x naught. And second point we have x1 and f of x1. So we call it that both these points has a slope, and we define it with m is equals to f of x1 minus f of x naught divided by x1 minus x naught. So using the point slope form of a line, we have y minus f of x is equals to, sorry, here we have x1 is equals to mx minus x1. So we set y is equals to 0 to find where this line intersects the x-axis. So we simplified it to 0 minus f of x1, that is equals to mx minus x1, and when we simplify it, we will get x is equals to x1 negative of f of x1 and x1 minus x naught over f of x1 minus f of x naught. So to set our next approximation x2 is, or we just simply say that the generic formula for secant method is x n plus 1, that is equals to x of n, and we have negative x n, xn minus xn minus 1, and divide it by f of xn and negative f of xn minus 1. So in this case, our n ranging from 1, 2, 3, and up to so on. Or we simply write this formula as x of n plus 1, that is equals to xn minus 1 f of xn minus xn, and we have f of xn minus 1 divided by, we have f of xn and minus f of xn minus 1. So we have n starting from 1, 2, 3, and up to so on. So this is the iterative formula for a secant method. So let's move to the basic topic of today's video, is the working rule of secant method. Let's now break this into a working rule or an algorithm. So the step 1, we need to choose two initial guesses, and let's suppose we have the first initial guess x naught and the second one is x1, and that is close to our root. Second step is compute f of x naught and f of x1. Thirdly, we need to apply the secant formula. So we have xn plus 1, that is equals to xn minus 1, f of xn minus xn and f of xn minus 1 divided by, we have f of xn minus f of xn minus 1. So here we need to just put n is equals to 1 in this generic formula, and we just shifted this generic formula into a customized formula. So it will become x2, x0, x naught basically, and f of x naught minus, sorry, it's not x naught, it should be x1, minus x1 f of x naught and divided by f of x1 minus f of x naught. In the fourth step, we need to update the values. X naught is equals to x1 and x1 is equals to x2. Now we need to repeat the step 2 to step 4. Until the required accuracy is achieved. It means that you have the value of xn plus 1 minus x of n is smaller than preset tolerance, and you need to define the tolerance according to your choice. So say you have a tolerance of 10 raised to the power minus 5 or 10 raised to the power minus 4 or 10 raised to the power minus 3. That's up to your choice. So this is the basic working rule of the secant method. So this iterative loop continue until we get close enough to the actual root of f of x is equals to 0. So the closer the initial guesses are to be the actual roots, the faster the convergence. So the key characteristics or the most important points about this method you all need to know is important points. So number one is no need of derivative for this method. Unlike Newton-Raphson method, which requires a computation of a derivative, and this method only needs a function value but not its derivative. That is the best part of this method. Secondly, super linear convergence. This is faster than bisection method but slower than Newton-Raphson method, but this is also a good balance. Thirdly, this is sensitive to initial guess. So poor guesses, not guess initial guesses. So poor guesses may cause divergence or slow convergence. So it's better choose initial guesses wisely. And the last one is its efficiency. So for well-behaved function, it converges rapidly and with less computational cost. So to sum up, the secant method is powerful root finding technique that bridges the simplicity of the bisection method with the speed of Newton-Raphson method, but without requiring derivatives. So it's particularly useful when the function is smooth and continuous, and secondly, you can provide two good initial guesses. We'll walk through step-by-step solution to the secant method using two different examples in which we go for detailed calculation and visual explanations that makes the concepts crystal clear. So whether you are just a beginner or revising for an exam, this video is your key to mastering this powerful root finding technique. So let's get started. So we have a question number one that find the solution of p is equals to cos of p by secant method correct up to 4 decimal places for the initial approximation p naught 0.5 and p1 is equals to pi by 4. First of all, we need to shift this nonlinear equation into f of p is equals to 0 format, and this is a nonlinear equation because a trigonometric function is involved. Secondly, we need to check that this initial guesses is brackets the root or not, because p naught is 0.5 and p1 is pi by 4. So we need to check that either our root is bracketed in these initial guesses or not. So let's start the solution. So we have p is equals to cos of p. So f of p is equals to p minus cos of p, that is equals to 0. After that, we need to put f of p naught into our equation. So it's become p naught minus cos of p naught. So that is equals to f of 0.5, that is equals to 0.5 minus cos of 0.5, and they give us a solution negative 0.37758. So this is a negative value. After that, we need to substitute f of p1. So we have p1 minus cos of p1. So we have f of pi by 4, that is equals to pi by 4 minus cos pi by 4. So we need to simplify it. After simplification, we will get 0.078291. So this is positive value and this is negative value. So we got on the opposite sides. So it means that this initial guesses are fine and the root lies in that range. Now let's go for the first iteration. So the customized formula for secant method is P2. In that case, we are choosing n is equals to 1. So P2 is equals to P naught f of P1 minus P1 and f of P naught divided by we have f of P1 minus f of P naught. So we need to substitute the values. We have the P naught that is equals to 0.5 and f of P1 is 0.078291 minus P1 is pi by 4 and we have f of P naught is negative 0.37758. So we need to simplify it, and in denominator we have f of p1 0.078291 and minus 0.3758. So we need to simplify it. After simplification, we get the value 0.73638843. So that is the value of P naught, and we need to substitute in the function in order to find out the value of f of P2. So f of P2 is equals to, we have the function P2 minus cos of P2. So that is equals to 0.73638843 minus cos of 0.7363843. So you need to simplify it. After simplification, you will get negative of 4.519622 into 10 raised to the power minus 3. After that, we need to go for second iteration. So for second iteration, the customized formula is, in that case, we need to substitute n is equals to 2 in our general formula. So the customized formula will be P3, that is equals to P1 f of P2 minus P2 and f of P1. And in the denominator, we have f of P2 minus f of P1. So we need to substitute the values. So the value of P1, we need to extract it from here. This is the value. So we have pi by 4, and f of P2 is, we have negative 4.519622 into 10 raised to the power minus 3 minus P2, we have the above value 0.733843 divided by, we have negative 4.519622 into 10 raised to the power minus 3 minus f of P1. So we have f of P1, this is the value, that is 0.078291. So you need to substitute here 0.078291. We need to just simplify it, and after simplification, we will get the value 0.739062. This is the value of P3. So we need to substitute in our function. F of P3 is equals to P3 minus cos of P3. That is equals to 0.739062 minus cos of 0.739062. So after simplification, you will get negative of 3.87158 into 10 raised to the power minus 5. Okay, so we need to keep in our mind that we need to go for 4 decimal places. This is our tolerance, defined tolerance. So for P2, we have 0.7363, and for P3, we have 0.7390. So we got the accuracy to 2 decimal places. So let's go for the third iteration. In that case, we need to substitute n is equals to 3 in our generic formula. So the customized formula will become P4, P3, f of P2 minus P2, f of P3 divided by f of P3 minus f of P2. We need to just substitute the values. So P3 is 0.739062. F of P2 is, previously, this is the value of f of P2. So we need to substitute it here. So it is minus 4.519622 into 10 raised to the power minus 3, minus we have P2. The value of P2 is 0.736383, and f of P3 is minus 3 point, we don't have a space, so I'm just shifting a little bit lower side, 3.871582 into 10 raised to the power minus 5, and divided by, we have f of P3, so that is negative of 3.871582 into 10 raised to the power minus 5, and minus we have negative 4.519622 into 10 raised to the power minus 3. So you need to simplify it. So after simplification, we will get 0.73908. So this is the value of P4. So we need to check either we achieve the accuracy to 4 decimal places or not. So the value of P3 to 4 decimal places is 0.7390, and P4 we have 0.7390. It means that we achieved the accuracy. So hence the correct route up to 4 decimal places is P is equals to 0.7390. Let's proceed to the second question. Okay, so we have a question number 2, that find the real root of an equation x cubed minus x minus 1 that is equals to 0. So the given equation is a nonlinear equation by secant method, correct up to 3 decimal places. Okay, in this question we are given with a nonlinear equation and a tolerance, but we are not given with the interval. So first of all, we need to find out the interval with the help of an hit and trial method. So we have the function f of x is equals to x cubed minus x minus 1 that is equals to 0. And I'm going to just start putting my values initially for x is equals to 0. So when I put 0, we will get negative 1. So that is a less than 0 value. Okay, let's check for x is equals to 1. So when I substitute 1, so it becomes cancel out, and we will get again negative 1 that is also less than 0. So 0 and 1 should not be the interval because both giving us a same sign. Let's go for 2. So when we substitute x is equals to 2, so it's become 8 minus 2 minus 1, and we will get positive 5 value. Okay, so we have two options, that either we choose an interval 0 to 2 because 0 gives us a negative sign, or 2 gives us a positive sign, so this is a fine interval, or the second option that we choose 1 to 2 interval, that is negative and that is positive. Now this is the smaller interval, but I just wanted to reduce the size of this interval so that the number of iteration will also be reduced. So for that case, I am just checking the middle values from 1 to 2. So I am targeting to 1.5. So after putting 1.5, we will get 0.875 that is greater than 0. Okay, let's go for 1.4 because I'm going to choose 2 points. So it should be 1.4 raised to cube minus 1.4 minus 1. So that is equals to 0.343. So that is also greater than 0. Let's go for 1.3. So f of 1.3, 1.3 raised to cube minus 1.3 minus 1. So the answer should be negative 0.10. Okay, so I am choosing 1.3 to 1.4 interval, and at 1.3 we get negative 0.103, and f of 1.4 we will get positive value 0.343. Okay, let's go for first iteration in order to achieve the accuracy till 4 decimal places. So in that case, I am substituting n is equals to 1. So the customized formula would be x2, that is equals to x naught, f of x1 minus x1 f of x naught over f of x1 minus f of x naught. So we have x naught, this is our x naught, and this is our x1. So 1.3 and f of x1 is 0.343 minus 1.4 and negative 0.103 divided by, we have 0.343 minus, and we have minus 0.103. We need to simplify it, and after simplification we will get the value 1.32304. We need to evaluate the function value also. F of x2, that is equals to x square cube minus x2 minus 1. So we have 1.32304 raised to cube minus 1.32304 and negative 1, and after simplification we will get negative 0.007136, that is less than 0. After that we need to go for the second iteration. Here we have n is equals to 2, and the customized formula is x3, that is equals to x1 f of x2 minus x2 and f of x1 divided by f of x2 minus f of x1. So we need to substitute the value. The x1 is equals to 1.4. We have negative 0.007136 minus x2, we have 1.32304, and f of x1 is 0.343. In the denominator part, we have negative 0.007136 and minus 0.343. After simplification, we will get negative 0.000481. No, sorry. It should be 1.324605. Okay, let's see till which decimal place we will get the accuracy. Okay, so that is the value of x3. Let's check the tolerance. So we have the value of x3, x2 is 1.3230. So here we have 1.324. So we achieved the accuracy to 2 decimal places. So let's move to the third iteration. In that case, we need to substitute n is equals to 3, and the customized formula is x4 x2 f of x3 minus x3 f of x2 divided by f of x3 minus f of x2. We need to substitute the values. So we have 1.32304 f of x3. Okay, we need to find the function value also. So here we have f of x3 is equals to negative 0.3 times 0, 481, that is less than 0. So we need to substitute here. 481 minus the value of x3 should be 1.324605, and f of x2 is negative 0.007136 divided by, we have negative 0.000481 minus, and f of x2 is negative 0.007136. After simplification, we will get 1.324717. Okay, so if we check, the value of x3 till 3 decimal places is 1.324, and the value of x4 is 1.324. So we achieved the accuracy after third iteration. So we can simply say that hence the correct root up to 3 decimal places is x is equals to 1.324. And there you have it, a complete step-by-step solution using the secant method from the initial guesses to the final root. So we have seen that how this method smartly avoids derivative and still gives an accurate results. Explore the mathematical proof behind the order of convergence of a secant method, and we will reveal that why it's more efficient than bisection method, but just a step behind Newton-Raphson method. So if you are a student, researcher, or just curious about this why behind the method, this is your deep dive into theory. So let's uncover the maths that makes the secant method tick. So let's get started. So as we know that the error of secant method is epsilon n plus 1, that is equals to k epsilon n and epsilon n minus 1, and we call it 1. This k is the constant of proportionality, and for nr method we have epsilon n plus 1, that is equals to k and epsilon n raised to p. So we need to find that number p. So we will find the number p and replace n by n minus 1 in equation 2. So it's become epsilon n, we need to replace n with n minus 1. At the place of n, we have n minus 1 plus 1, that is equals to k epsilon n minus 1 raised to p. So this will cancel out, and after that we have epsilon n, that is equals to k epsilon n minus 1 raised to p. Okay, we need to take the power on both sides 1 over p. just to simplify the expression. So it's like that, and we have P also. After that, we will have epsilon n 1 over P, that is equals to K 1 over P, and epsilon n minus 1 P into 1 over P. So this P cancel out with this P, and here we have 1 over P, that is equals to K 1 over P and epsilon n minus 1. So we know that K is the constant of proportionality. So we are just replacing K 1 over P with C. Our equation will become epsilon n 1 over P, that is equals to C, and epsilon n minus 1. From here we need to separate epsilon n minus 1, so it's become epsilon n minus 1 is equals to 1 over C and epsilon n 1 by P. So we call it our equation 3. Now we need to put equation 2 and equation 3 in equation number 1. Putting equation 2 and equation 3 in equation 1. So this is our equation number 1. So we are going to replace this equation 2 and the equation 3 that we found from here back into equation number 1. So as we know that the equation number 1, we have epsilon n plus 1, that is equals to K epsilon n and epsilon n minus 1. So let's become, after replacing the values, we have K epsilon n P, that is equals to K epsilon n. It remain as it is, and here we have into 1 over C epsilon n 1 over P. After that, we need to just simplify it. We have K epsilon n raised to P. This K and this 1 over C is the constant of proportionality, so we are just compiling it together. Here we have epsilon n and epsilon 1 by P. So bases are same, so powers is going to be added. It's become K over C epsilon n 1 plus 1 over P. I'm just going to take the LCM of the powers. So we have epsilon n raised to P, that is equals to K by C epsilon n P plus 1 divided by P. After that, we are going to equate the powers. So we have P is equals to P plus 1 divided by P. So I am just simplifying it, multiplying this P with this side. So it's become P square, that is equals to P plus 1. And after that, we have P square minus P minus 1, that is equals to 0. Now we need to apply the quadratic formula on this quadratic equation. So we have the quadratic formula P is equals to minus B plus minus B square minus 4AC divided by 2A. So according to this equation, we have A is equals to 1, B is equals to minus 1, C is equals to minus 1. So we have P is equals to minus 1 plus minus 1 raised to square 4 into 1 into minus 1 divided by 2 and 1. So we need to just simplify it. P is equals to 1. This minus and minus become positive. And here we have 1 and plus 4 by 2. So after simplifying, we have 1 plus minus under root 5 by 2. So from here, we have two roots, 1 plus under root 5 by 2. And secondly, we have P is equals to 1 minus under root 5 by 2. And we know that P is an order, and order is always positive. So we are neglecting the negative root. So we are just considering P is equals to 1 plus under root 5 by 2, and if we solve it and convert into a decimal, so we will get 1.618. So according to this, we say that therefore the order of convergence of secant method is 1.618. And there it is. The secant method converges with an order of approximately 1.618, the golden ratio. Not just a cool number, it's a symbol of elegant efficiency in numerical analysis. Explore the Newton-Raphson method consistently outperforms the secant method. And we will back it up with graphical intuition, error analysis, convergence order, and real life reasoning. So let's dive into the maths behind the method and see why Newton-Raphson method takes the crown. So let's get started. So first one we have graphical behavior, and starting point. So graphically, the Newton-Raphson method uses the tangent line at the point to jump closer to the root, while in case of a secant method, uses a line between two previous points. So this gives NR method an immediate edge and the derivative of the functions allowing faster and more accurate steps. Secondly, we have the convergence speed, and we know that Newton-Raphson method has quadratic convergence. So if we talk about the strength of Newton-Raphson method, so Newton's Raphson method biggest strength is its quadratic convergence. So the error shrinks proportionally to the square of the previous error. So this means that once you are close to the root, each step rapidly increases accuracy. So in contrast, the secant method only has superlinear convergence, with an order of about 1.618. So that's fast, but not nearly as fast as Newton-Raphson method. Thirdly, we have the error analysis. So let's look the error formula for Newton-Raphson method. The error at each step plus 1 is proportional to the square of the previous error, like for NR method. For Newton's Raphson method, En plus 1 is proportional to epsilon n raised to square. So that is basically the error at each step n plus 1 is proportional to the square of the previous error. So that's powerful. Each new error shrinks dramatically. On the other hand, the secant method depends on two previous errors. For secant, we have epsilon n plus 1 that is directly proportional to epsilon n and product with epsilon n minus 1. So that's why its convergence is little bit slower than Newton-Raphson method. So numerically speaking, NR method has a convergence of order 2, or we just simply say that rate of convergence is 2 for NR method or a Newton-Raphson method. And for secant method, the rate of convergence or order of convergence is 1.618. That is little bit slower than Newton-Raphson method. So this proves mathematically that Newton-Raphson method is superior in speed and precision. Let's talk about the fourth point about the derivative requirement. So now, to be very fair, the secant method does not require a derivative. This is useful when the function is too complex to differentiate, and it's more accessible in some cases, but that comes at the cost of efficiency and accuracy. So the fifth one, we have stability and practical applications. So we have stability and practical applications. So with a good initial guess, Newton-Raphson method is more stable and predictable than secant method. That's why it's used in real world engineering, physics simulations, and control systems. Because it reaches highly accurate answers in just fewer steps. So Newton's Raphson method is favored in time sensitive or high precision applications. So if we talk about the summary of all this discussion, so we have the features, we are talking about the summary, and here we have Newton-Raphson method, and then we have a secant method, so if we talk about the first feature that is the convergence order, so the convergence order for Newton-Raphson method is 2, so we just simply call it a quadratic convergence. Secondly, for secant method, we have 1.618 and we just simply call it a superlinear convergence. Secondly, we have the derivative requirement. So for derivative requirement, for Newton-Raphson method, definitely derivative is required, and for secant method, we don't need any derivative calculations. Thirdly, we have the error analysis. So for error analysis, the for Newton-Raphson method, the error is proportional to the square of previous term, and for secant method, the error is proportional to the previous two term. One is epsilon n and the other is epsilon n minus 1. If we talk about the accuracy, then the accuracy of Newton-Raphson method is very high, and the accuracy of secant method is moderate. Finally, if we talk about the practical applications, so for Newton-Raphson method, the NR is very useful in engineering, real-time applications. For secant method, the practical application is for those applications where derivative is unknown. So when derivative unknown. So when it comes to speed, accuracy, error control, and practical power, Newton-Raphson method stands tall. So it's mathematically proven to converge faster and more precisely. In the end, both methods have value, but the Newton-Raphson method is the undeniable winner when performance matters most. We are going to explore the advantages and disadvantages of the secant method, a powerful technique used in numerical analysis to approximate the solutions to equations. So let's get started. Let's first talk about the advantages of the secant method. So what makes it attractive? So initially we have the advantages. So the first advantage of a secant method is that no derivative required. Unlike the Newton-Raphson method, you don't need the derivative of the function, firstly. Secondly, that is a very big win when derivatives are hard to compute or don't exist. So this makes the secant method more flexible. Second advantage is that requires only one function evaluation per iteration. Requires only one function evaluation per iteration. With Newton-Raphson method, you need both the function and its derivative at every step, or you simply call it at each iteration. So here just one function evaluation per iteration is enough. That is faster and more efficient computationally. Computationally. With Newton-Raphson method, you need both the function and its derivative at every step, or you simply say it at each iteration. So here just one function evaluation per iteration is enough. So that makes it a faster and more efficient computationally. Thirdly, we have faster than bisection and regular policy method, or we simply say it faster than bisection and regular policy method. So the secant method is generally faster than other bracketing methods, though its convergence is not quadratic like the Newton-Raphson method, but it's better than linear convergence, and we often call it superlinear convergence. Fourthly, we have simple algorithm. So with two initial guesses and simple formulas, it's relatively easy to implement. But of course, the secant method isn't perfect method. So let's move to its disadvantages. So the first disadvantage is that it requires two initial guesses. You need two initial approximations, unlike Newton-Raphson method, which start with just one. If your guesses are far from the root, convergence may fail for this case. Secondly, we have not guaranteed to converge. So there is no guarantee that this method will always work. If the function is poorly behaved or your guesses are bad, the method might diverge. Third disadvantage is that may fail if function values at 2 points are equal. Look at this point. If f of xn, that is equals to xn minus 1, the denominator part in the formula becomes 0 if both of these points going to be equal. So this causing division by 0 and the method fails. So to sum up, if you want a method that's efficient and doesn't need any calculus and performs better than basic bracketing methods, the secant method is a great choice. But just be cautious with your initial guesses and always watch for function behavior. We will implement this secant method in MATLAB step by step. So let's get started. So for the development of the secant method code, we need the following things. Number one, we need to define our nonlinear function. And in that case, we are choosing x cubed minus 2x minus 5. Secondly, we need to set the two initial guesses, that is x naught is equals to 2 and x1 is equals to 3. After that, we need to apply the secant method in order to find out the root. So for that, we are using the while loop. Next, we need to check the convergence based on the tolerance. So that should be 10 raised to the power minus 6. After that, we are going to plot the function. And finally, we need to display the final root and its results. So let's move to the MATLAB. Okay, so this is the interface of the MATLAB, and we need to just click on our new script. So an editor pop up in front of us, and we are going to develop the code of secant method. So this is our secant method script. So initially, I'm going to start it with CLC, clear all and close all. After that, we need to define our function. And here we are choosing f is equals to at the rate x, and the function should be x raised to cube minus 2 static x minus 5. That is our function that we are choosing. After that, we need to define our initial guesses. So the first initial guess is x naught is equals to 1, and the second one is x1 is equals to 3. Sorry, we are choosing x naught is equals to 2. That would be our first initial guess, and this would be our second initial guess. Okay, after that, we need to define our tolerance, and here I am choosing 1 e raised to the power minus 6. So that is basically the tolerance for convergence. After that, we need to define the max iteration. So here I am choosing max iteration to 100. So that is basically the maximum number of iterations. After that, we need to initialize our variables. So we are just initializing iter, that is 0, that we are going to use in the loop. So that is basically the used as an iteration counter. After that, we need to write down the loop. So here is secant method loop. So I am choosing a while loop. So for while loop, I am choosing iter must be less than max iteration. And initially, I am going to compute the first approximation using the secant formula. So compute the next approximation using the secant formula. So the secant formula should be x2 is equals to x1 minus f of x1 static, and we have x1 minus x naught divided by f of x1 minus f of x. So that is the formula of a secant method. After that, we need to check that if the result is within the tolerance or not. So check if the result is within the tolerance or not. So for that, I am using if condition, that if ABS, that is abs x2 minus x1, that should be less than tolerance. So after if statement, I'm going to use my AND, and in between I have to print, so f print f and root found at x is equals to percentage dot 6. I'm using here dot 6 because we need to check the tolerance to 10 raised to the power minus 6. So that's why this will display the number still 6 decimal places. So after percentage d iterations dot backslash n, and we have to show x2 as a result, and the counter should be iter plus 1. So after that, it break it, and then we need to end it. After this, we need to update our variable for the next iteration. So we have x naught is equals to x1, x1 is equals to x2, and finally we have iter is equals to iter plus 1. So that is basically increment the iteration counter. Okay, that's it in the while loop. So after that, we need to check that if the method did not converge within the maximum iteration. So for that, we need to use an if statement. So if iter is equals to max iteration, so the print for us that method did not converge after percentage d iterations dot backslash n, and we have to max iterations. Okay, after that we need to go for some plotting commands. So initially we are going to plot our main function. So plotting the function. So for that we need to define our x and y values initially. So x values should be linspace, and that is 1 to 4 to 100. So that will basically generate x values for the plot. After that, we need to generate the y values. For that, we are using array function. So array function, we have the first function, that is our nonlinear function, and we have x values. So that will basically evaluate f of x for each x. Then we need to open our figure, and after that we need to plot our main function. So x values versus y values, and we are just defining the color and the style, and the color should be red and the style should be a solid line. After that we need to define the line width, that is totally optional, it's according to your choice. So we need, this will plot the function f of x. After that we need to use hold on, and we need to plot the roots. So we have x2 versus f of x2, and we have to choose the color and the style. Color is blue and style is circle, and as we are using a circle, so we need to define a marker size just to prominent it. Marker size should be set it to 10, and the marker face color, that should be fill this circle. So we are just choose the color of the marker face is blue. So that will basically plot the root. After that, we need to just customize our plot, and for that, we need to define the X label. And for that, I'm choosing X. Then we need to define the Y label. So for that, we are choosing f of X. After that, we need to define the title. So that is the MATLAB code for secant method. After that, I want to on my grids. And finally, we need to define the legend. So the first is of f of x. That should be our red line. And then we have a root. That should be our filled blue dot. Okay, let's run it. This is a secant method. Okay, we need to fix our error first. And we have an error in legend, so L should be small. We need to run it again. Okay, so finally we found our root at x is equals to 2.094551 after 6 iterations. And this should be our graph of secant method. This red line represents the function, that is our f of x, and this blue dot represents the root that we found by using a secant method. And that's it. If you found this video helpful, be sure to like, subscribe, and hit that notification bell so you don't miss out any numerical techniques that is coming your way. So drop your questions or feedback in the comment. I would love to hear from you. So thank you so much for tuning in. I'll see you soon in the next video. Take care.